Okay, now that we have a molecule of succinate, we can oxidize it. And the oxidation results in the formation of a double bond from this single bond in the internal. This reaction is catalyzed by an enzyme called succinate dehydrogenase. And not surprisingly, right, since we oxidized this carbon chain, we can reduce something else. Now, it's not NADH, which is surprising. We're going to introduce a new cofactor here called coenzyme Q, sometimes abbreviated Q. It can also hold electrons, just like NAD8 or NAD+. And when it becomes reduced, it forms a molecule of what we call QH2. QH2 we think of a lot like NADH. It's a reduced cofactor, holds electrons, just has a little less potential energy than NADH. It will end up in the electron transport chain and oxidative phosphorylation, producing less ATPs than an NADH because it has less potential energy. It's easier to get those electrons on there. And so this oxidation reaction can unload electrons onto Q. It wouldn't be able to do it onto NAD+. And so we've got a different reduced cofactor here, but we need to think of it sort of as a weaker cousin to NADH. Okay, now that we've got, right, this molecule, which I haven't named yet, this is called fumarate. We can convert fumarate to malate, and we're almost home here. We're almost finished our cycle. Malate is generated through a hydration reaction, and hopefully you remember hydration reactions from organic chemistry. We have an alkene here in fumarate, and so we can add a water across that double bond. It's not going to be Markovnikov or anti-Markovnikov since these carbons are equivalent to each other, but we're generating an alcohol from this. This carbon got the OH. This carbon got the hydrogen, and we end up with our 4-carbon malate molecule. Okay, now here we go. This completes our circle. Wait, I keep forgetting these enzymes. This enzyme is fumarase. The last enzyme to convert malate to oxaloacetate is our malate dehydrogenase. Okay, malate dehydrogenase is a dehydrogenase, and we do have an oxidation reaction. We're taking this alcohol, we're turning it into a carbonyl. You know, this carbonyl is down on a different carbon, but it doesn't matter. You can see these are symmetrical, so that would be the same molecule. And not surprisingly, since we're oxidizing and using a dehydrogenase, we're generating another molecule of NADH in the mitochondria. Okay, so this completes our cycle, right? We have, let's try another pen here. Reaction 0, right? Our pyruvate dehydrogenase complex, citrate synthase, aconitase, isocitrate dehydrogenase, alpha-ketoglutarate dehydrogenase, our succinyl-CoA synthetase, 5, succinate dehydrogenase, 6, fumarase, 7, malate dehydrogenase, 8. Those are the 8 reactions of the Krebs cycle, plus our reaction 0 of pyruvate dehydrogenase complex. Again, we've got our 3 carbons of pyruvate getting converted to 2 carbons of acetyl-CoA. Those 2 carbons get popped off one at a time, and we go back through the cycle. And so we can think of acetyl-CoA as being the fuel that's being shoveled into the Krebs cycle, being oxidized to generate these reduced cofactors, plus some straight up energy as a GTP. Okay. Let's do a little accounting if we can. Up in the corner, right? So for 1 glucose, we generate 2 molecules of pyruvate. And those 2 molecules of pyruvate turn into 2 molecules of acetyl-CoA. Okay, these acetyl-CoA molecules both go through the Krebs cycle. And let's think about accounting here. We know about glucose going to pyruvate, so I'm not going to go over that again. As we move 2 pyruvates to 2 acetyl-CoAs, we generate 2 NADHs. As each acetyl-CoA, or as 2 acetyl-CoAs go through the Krebs cycle, you'll see there's 1, 2, 3 NADHs for each acetyl-CoA. So we generate 6 NADHs. We make a GTP for each acetyl-CoA, so 2 GTPs. And we generate 2 QH2 molecules. Okay. I guess the last thing, let's account for glucose to pyruvate, just to make one last point. We know as we make 2 pyruvates from 1 glucose, we generate 2 ATPs and 2 NADHs. I'm going to put a star by those NADHs. Again, those are cytoplasmic NADHs, while these NADHs here are mitochondrial. And the electron transport chain is in the mitochondria, so these guys are where they need to be. We're going to have to waste a little bit of energy to get these cytoplasmic electrons and these NADHs generated in glycolysis into the mitochondria to harvest ATPs from them.